Human engineering is a constant battle against extreme stress. When we try to build engines that run hotter or structures that hold more weight, standard metals like iron and copper simply warp, snap, or melt. To survive these absolute extremes, engineers looked to a specific vertical slice of the periodic table, Group 5. These D-block transition metals share a defining atomic blueprint. Every single one has exactly 5 valent electrons in its outermost shell. That specific 5-electron configuration allows them to form incredibly strong metallic bonds. This results in extreme physical density, massive melting points, and the ability to exist in multiple oxidation states, meaning they can easily share or trade electrons with other elements without breaking down. This atomic layout is the absolute prerequisite for building technologies that refuse to break under pressure. At the top of the group sits element 23, vanadium. As the lightest member, it acts as the ultimate industrial enhancer. A tiny fraction of it is all you need to reinforce the skeleton of a skyscraper. When you mix vanadium into steel alloys, it acts as a catalyst. The resulting metal is highly durable and capable of withstanding the immense rotational stress inside jet engines and heavy-duty mechanical tools. Moving one step down the column to niobium, element 41, increases the atomic mass and expands the physical capabilities of the group. Niobium enables complex physics beyond structural reinforcement. When cooled, it loses its electrical resistance entirely. This allows it to carry the massive electrical currents needed to generate powerful magnetic fields, making it a critical component in superconducting magnets like those used in MRI machines. A single square's descent down the periodic table adds the capacity for advanced medical electromagnetism to the materials industrial toolkit. This chart compares standard metals to element 73, tantalum. Iron and copper melt far lower, while tantalum requires a staggering 3,000 degrees Celsius before turning to liquid. This extreme resistance means it is completely chemically inert, simply not reacting with most other substances. Because it won't degrade, engineers rely on tantalum for zero-failure environments. It protects tiny electronic capacitors in your electronics, and it serves as the perfect material for human surgical implants, safely resisting biological corrosion inside the body. We've seen strength, magnetism, and total chemical resistance. So what happens to this blueprint when we push the atomic mass down one more row to element 105? We get dubnium, a synthetic element created in a lab. At this extreme mass, the atomic rules of the group completely break down. The nucleus of dubnium is so heavily packed with protons and neutrons that it cannot hold itself together. It decays almost instantly, making it highly radioactive and leaving it with zero commercial applications. Exploring Group 5 shows us the absolute peak of physical resilience in the natural world, right up until the exact moment the atomic structure fractures under its own weight. Group 5 is an escalating ladder of structural resilience. Adding mass to that exact same 5-electron blueprint makes increasingly extreme human technologies possible, from building cities to probing synthetic physics. The next time you look at a towering skyscraper or step inside an MRI machine, recognize that the hidden strength holding our modern world together relies entirely on the precise arrangement of just 5 electrons.